we've talked about adding and subtracting vectors with one another. We've talked about multiplying a vector with a scalar, but we haven't talked about combining two vectors. Because vectors have their own unique mathematical operations, there are special rules, special operations we have to do to combine vectors for different purposes. One of the vector operations that we're going to need to know in the upcoming chapters is the vector dot product. The vector dot product is a vector operation. This operation has exactly two vectors to input, and it gives us a resulting scalar value. This scalar value that it gives us is related to the angle between the input vectors. What it's doing is it's projecting one vector into the direction of the other. Another way to think of what a vector dot product gives us is a measure of how aligned or how parallel the two input vectors are. If the two vectors are more parallel or more anti-parallel, if they're closer to being aligned, the value of the dot product will be larger, and if they are closer to being perpendicular, the value will be smaller, or will be 0 if they're perfectly perpendicular. If the two vectors tend to be parallel means that they are generally in the same direction, you'll have a positive dot product. If the two vectors tend to be anti-parallel, meaning they're generally in opposite directions, you'll have a negative value of your dot product. So in 2 dimensions, we'll assume 2 dimensions, but this works in 3 dimensions as well. In 2 dimensions, you've got your two vectors here, and you've got this angle is theta. Theta is the angle measured from vector A to vector B. And one way to express the vector dot product is to say that this quantity is the magnitude of vector A times the magnitude of vector B times the cosine of the angle between those two vectors. So if you know this quantity, you know the magnitudes, you can find the cosine of the angle between the two, you can find and use inverse cosine to find the angle between those two vectors. Another way to find the vector dot product is this equation here, ax bx plus ay by plus az bz. So in this case, you are multiplying the corresponding components in each direction and then adding the results. If the vectors are only 2-dimensional, then their z components would be 0, and that term would just go away. If any of the other components are 0, you're going to do the multiplication just like normal. A couple of rules about the vector dot product. It's a symmetric function. Being a symmetric function, it means that a dot b is equal to b dot a, because if you swap the order of multiplication here, b dot a would be bx times ax plus by times ay, and so forth. That is the exact same quantity. If you dot a vector with itself, a dot a, that would be ax plus ay plus az. That would be ax squared plus ay squared plus az squared. That is the magnitude of the vector A quantity squared. And finally, if you are taking the dot product of two unit vectors, I dot I would be 1, j dot j is 1, k dot k would be 1, I dot j would be 0, I dot k would be 0, and so forth. If we go back up to this version here, we can see that if we have I hat dotted with I hat, that would be the magnitude of I hat is 1, the magnitude of I hat is 1, and the cosine between I hat and I hat, the angle between I hat and I hat is 0, cosine of 0 is 1, and 1 times 1 times 1 gives us a factor of 1. I hat and j hat are 90 degrees apart, so cosine of 90 degrees would be 0, and that's why we get that value to be 0. So you can think of sort of distributing the dot product, and when you distribute the dot product, the corresponding components all survive, and all of the cross components, all of the components that are the x component of A and the y component of B, for example, would cancel out and give us 0. A way to visualize what's going on here is to look at a diagram like this. Here I've got a vector A in blue and a vector B in green, and there's this angle theta AB that is measured between vector A and vector B. And so what I can do is I can take my vector A and I can project vector A into the direction of vector B. This is the component of A in the direction of vector B, and by rearranging this equation for the dot product, we can say that this component of vector A is the magnitude of A times the cosine of the angle between the two. But we also said that the cosine of the angle between the two would be A dotted with B divided by the magnitude of A times the magnitude of B. Those two terms cancel, And what we can do here is find how much the magnitude of vector A in the direction of vector B would be this scalar quantity, this number that we would get. The same thing is true. The component of vector B is, vector B has a component that is in the direction of vector A, and we could use the same math to find out how much of vector B is in the direction of vector A by applying this dot product. And so we use this a lot when we have multiple vector quantities. We can project the vector, one of our vector quantities, into the direction of another vector quantity using the dot product here. If we know the dot product, we can find the angle, or if we know the angle, we can find the components.